Welcome back everyone. In this lecture, we will continue with the group action, and then first let us define some basic terminologies, and after that we will focus on this orbit stabilizer theorem. Okay, let's fix some notations before beginning. As before, let us take G be a group and X be a non-empty set. So now let's say G acts on X via some group homomorphism tau. Okay, so G acts on X, let's say via tau. So what is tau? Tau is a group homomorphism from G to Sx. Okay, so now with this data, what we want to actually define, there are few things that one can define both related to the group as well as the set. So let us first define what is called an orbit. Okay, so let us fix some element x in capital X. Okay, so this is the element that we are fixing. So then what we want to do, so let's say diagrammatically, so this is our capital X, and then you have chosen this element small x in capital X. So what we can do now, so for given G, so you have this tau G, so which is a permutation of capital X. Okay, in particularly we can look at the image of this small x under this tau G. Okay, so let us see what happens. So this is tau G of x. So in shorthand notation we denoted it by G dot x. Okay, and now what we can do, we can vary this G in capital G. So we can trace out all possible images of this x under the elements of capital G. So that is called the orbit of x. Okay, so the orbit of x, so which is has many notation in the literature. Okay, either it is written ORB of x or OX. So we will use this notation OX. Okay, this is the notation we are going to use. So this is by definition. So you look at all possible images of this x under this action of elements of capital G. Okay, so you look at G dot x where G in G. So this is called orbit. So for example, if G is finite group, then what will happen? So there are only finitely many elements in capital G. So if you look at the orbit of this x, so then it can be at most finitely many, because you are looking at images of this x under the action of capital G, but capital G itself is finite. So you can have only finitely many. Okay. So note, if the group is finite, then the orbit is also finite. Okay. So now here is another important terminology. So sometimes we are interested in understanding, okay, what how big this orbit and so on, exact cardinality of the orbit. Okay. So we will see in a minute these orbits, okay, for different x's, different elements of capital X. So that will actually form a partition of this capital X, okay, where that x actually runs over some particular indexing set. Okay. So that is a very important property of this orbit. So maybe let us actually prove this. Okay. So here is the theorem. So this is called orbit decomposition. Orbit decomposition of capital X. Okay. So let us see what we are getting. So for x in X, we have this orbit of x. Okay. So if we take, let us say this x, so this is x, and if you fix some small x, then what we are seeing, we are actually looking at all possible orbit of this and so on. So, then that will form some subset. Okay. So, what we will prove actually these things that we are forming. So, if you take y and then g dot y and so on. So, these things z, g dot z and so on. So, these things will form a partition of capital X. So, recall what is the partition? Partition is a collection of subset of capital X. Okay. They are all mutually disjoint and whose union is capital X. Okay. So, we need to prove two things. Okay. So, we want to say that the orbits. Okay. So, now we need to collect these orbits. Okay. From some, so we have to choose some representatives of these orbits. So, the representatives you have to choose very carefully, okay, because you want to choose representative from each and every orbit, exactly one from each orbit. Okay. So, let us say that is chosen. Okay. So, it is easy to write it in English, then maybe I will rewrite it in mathematics. Okay. The set of orbits that is the collection O x, x in x. Okay. For example, O x can be equal to very well be O y. Okay. So, this will form a partition of capital X. Okay. So, to prove this, there are two things one need to prove. The first thing is, okay, the union of the orbit is exactly x, and the second thing is, if O x intersection O y is non-empty, then that should imply O x equal to O y. So, these are the two things that actually defines a partition. So, the first one is obvious. Okay. Why? Because x is always there in O x. What is O x by definition? It is all the images of x under the action of capital G. So, note that if I take E dot x, that is exactly x. Okay. So, that is why x is always in the orbit of x. So, in particularly union of orbits will be capital X. So, this is obvious. So, now we will check the second part. Whenever there is some element in the intersection, then O x must be equal to O y. Okay. So, let us prove the one way. So, let Z is in this O x intersection O y. If we prove this implies O x is subset of O y, then we are done by symmetry, because from similar thing we can see that if Z in O y intersection O x, then that would imply O y is contained in O x. Okay. Using symmetry, then this would imply immediately that O x equal to O y. Okay. How do you check this? So, let us see how to check this. So, start with some element in O x. So, let us say that is g dot x. Okay. So, for some g in g, those are all the elements in O x. But note that Z is in O x. So, Z can be written as some g 1 dot x, and since Z is also inside O y, this can be written as some g 2 dot y. Okay. So, now what we need to check, okay, let us call this element x dash. Okay. We want to say that x dash is also element of O y. Okay. So, this x dash, to prove that, okay, this is the claim, this is an element of O y. Okay. So, that means we need to find some h in capital G such that x dash equal to h dot y. So, this is what we need to find. Okay. Such h we need to find. Okay. We have to find that using this information. Okay. So, let us see how one can do this. So, first of all, note that this x is indeed related to y. Okay. So, you can take this z on x which is equal to z to y. Now, by applying g1 inverse on both sides, what we get? G1 inverse dot G1 dot x, okay, that is going to be G1 inverse dot G2 dot y. So, now this is same as, okay, this is applying tau G1 inverse on tau G1 x, okay, this is exactly tau G1 inverse applied on tau G1 of x. But what it is? It is, you know, that tau G1 inverse composition tau G1 of x. But tau G1 inverse is nothing but tau G1 of inverse, okay, or this is, you can see that this is exactly same as tau G1 inverse composition or the product inside the, okay, let us not put the product here, just product in the group which we just denoted by G1 inverse G1 of x. But this is nothing but what? This is exactly tau identity of x, but tau identity, recall, it is just identity. Okay. So, tau identity is just identity on capital X. So, that proves that x is exactly equal to tau G1 inverse composition tau G2 of y. So, that means this is G1 inverse dot G2 dot y. So, this is what we are getting. Okay. So, that means in some sense x is in the orbit of y. Now, if x is itself in the orbit of y, then if you take any other conjugate of x, okay, all these elements g dot x, they are all called conjugate of x. Okay. So, that will be again inside this, okay, because now you see x dash is what? X dash is g dot x. So, then you can see that this is exactly g dot G1 inverse dot G2 dot y. So, that means x dash is nothing but g dot G1 inverse, okay, maybe rewrite this G1 inverse G2 dot y, which is in the orbit of y. Okay. So, that proves that orbit of x is always contained in orbit of y if the intersection is non-empty. By symmetric, we get again orbit of y. Okay. So, by symmetry or the similar arguments, we get orbit of y is contained in orbit of x, that implies orbit of x equal to orbit of y. Okay. So, this means if you take two orbits, either they are disjoint or they are equal. Okay. That is what this statement says. Okay. So, now what we have done? So, we have taken this capital X and then we have used this orbits, okay, to actually partition this capital X into some proper subsets of capital X. So, this is a partition of this. Okay. So, you have partitioned capital X into small orbits. So, now if you think about it, okay, now we need this parametricing set. Okay. So, this is actually a standard notation that one can use. Okay. So, this x mod g, okay, as before that we have introduced this in the quotient group, okay, or quotient set. So, motivated from that, okay, we are defining this x mod g to be the set of all orbits of capital X with respect to the action of capital G. Okay. So, this is my collection. So, what is x mod g? X mod g is all the orbits O x, x in G. So, now since this x mod g, okay, we can identify this with, okay, bijectively some subset capital lambda of x. So, how one can do this? Okay, this is the bijective correspondence. So, this is just bijective correspondence. So, what I want to do? I want to pick one element from each orbit, okay, using this axiom of choice. You can always do this, okay. This is using axiom of choice. So, what you can do? You can pick one element here x, here z, here y, and then here u, so that you form this capital lambda, okay. So, what is this capital lambda? Capital lambda choose subset of capital X such that capital lambda intersection the orbit is singleton. The cardinality of this is singleton for all x in capital X, okay. Or you can also say something like this: for all only the orbits matters, OX inside your x mod g. So, because of this, there is a natural bijective correspondence between capital lambda x mod g, which is just given by you take x and then send it to the corresponding orbit, okay. So, sometimes we identify this x mod g with capital lambda and work with that, okay, or sometimes we work with capital lambda. So, it will be very important to determine what is this capital lambda. We will do that in many of the examples that we have seen earlier, okay. But this is something very important, okay. So, in particularly when I write this orbit decomposition, so I write x as, so let us say disjoint union, this symbol means disjoint union OX, where x indeed comes from capital lambda. So, this is just the indexing set, okay, which is chosen such a way that this capital lambda intersection OX is the cardinality is 1 for all orbits, okay. So, this also sometime we write it this way, disjoint union OX, where OX runs over x mod g, okay. Sometimes we identify capital lambda with x mod g. So, we rewrite the same thing as x equal to disjoint union OX x in x mod g, okay. So, it is understood what it means. For example, if you are not comfortable with this identification, you can put x bar if you want, okay. But let us not use this, maybe like to emphasize what we are indeed doing, let us use this, okay. So, this is what we are going to use. So, this is called orbit decomposition of capital X, of course with respect to the action G. So, now this is something very interesting decomposition, because using the action of the group we have divided X into smaller subsets. So, they are just orbits, okay. But let us say you are interested in counting the number of elements in capital X, okay. Let us say the cardinality of X is finite, that is X is a finite set. Then what is this orbit decomposition says immediately? Then the cardinality of X is exactly summation the cardinality of the orbit where X runs over this capital lambda. Okay, in order to actually understand what is the cardinality of X, so it is enough to understand what will be the cardinality of these orbits, and of course what will be this indexing set. So, both informations are needed in order to actually calculate the cardinality of X. So, that is what actually motivates us to actually look for what will be the cardinality of this orbit X. For example, like I said, when G is a finite group, okay, then the orbit is always finite, okay, because the number of elements here coming from only the images of elements of capital G, Okay. So, since capital G is finite, so there are only finitely many images. So, let us see how one can actually compute the cardinality of this orbit, okay, when orbit is finite. But before that, let us make this observation. Okay. So, we have a very important group, okay, that is lying there uh, or underlying in for any orbit. Okay. What is that group? Again, fix x in capital X. Okay. So, first let us understand, okay, when two orbits can be equal. Let us say orbit of x is same as orbit of y. So, what is the meaning of that? Okay, one can check this is if and only if. Okay. So, this is something I will leave it to you. So, this is something I already proved off of it. Okay. So, because by symmetry other off is clear. So, orbits are same if and only if y is equal to some g dot x for some g in g. Okay. So, it is exactly the same proof, okay, because if y if O x equal to O y, then y is in O y. So, y must be some g dot x, but if y equal to g dot x, then it is easy to prove that O y must be subset of y x. Okay. And now, if y equal to g dot x, then it is easy to see that x is also in the orbit of y by applying g inverse on both sides, because y equal to g dot x if and only if g inverse dot y is exactly x. So, using this property one can verify that this whenever y is conjugate of x, then O x is also like x will be conjugate of y, then O x is also subset of O y. So, we already introduced what is called equivalence relation. Okay. If we think about it, so this definition is actually gives us what is called equivalence relation on capital X. Okay. So, this is something I will leave it to you to check. Okay. So, we are defining this relation. Let us define this tilde g. So, this is a relation. Okay. Relation tilde g on capital X. So, what is this? So, this is you say x for x comma y in capital X, we say x is related to y if and only if y is just conjugate of x, y equal to g dot x for some g in g. Okay. So, this is our definition of the relation. So, I will leave it to you to check. This is indeed tilde g is on equivalence relation. Okay, that is not very hard to see. So, you need to check this is actually reflexive, symmetric and transitive. Okay. So, now using the group property you can verify this. Okay, it is very similar to what we did the left multiplication of the group in the group itself. Okay. So, that is why I do not want to again check it. Now, what is important for x in, so this is the first one, the second one for x in capital X, if you look at the equivalence class, okay, that is those y in capital X such that y related to this x under this relation. So, that is exactly the orbit of x. Okay. So, this is something you can check directly from the definition. Okay. Both are easy to check. So, I will leave it to you. So, in particularly this also tells, because equivalence classes you know that they form a partition. So, in particularly this actually gives you the set of orbits gives you partition of capital X. So, now let us try to understand how one can approach the orbit of x. Okay. So, this tells you that whenever y is in orbit of x, then y must be equal to some g dot x. Okay. So, if you are interested in counting the elements of orbit of x, so let us say the cardinality of G is finite, let us say some n, then definitely the orbit of x can be written as G1 dot x etc. Gn dot x, okay, where G is listed as G1 etc. Gn. But obviously what happens, this will be over counting, because for some Gi's, okay, so the images can be equal. So, for example, some G dot x can be equal to G dash dot x, okay. So, in that case we are indeed over counting this set, okay. So, we need to be very careful. So, let us see when that can happen. If G dot x is same as G dash dot x, so then let us see what happens. Then you can easily see that this would imply x equal to G inverse G dash dot x. By applying G inverse on the both side, you can see that x is same as G inverse G dash dot x. That means what? That means this particular element that actually fixes this x, okay. So, that is something very interesting. So, that motivates us to define what is called stabilizer of x or Gx, okay. We use both notation. What is this? This is those elements of capital G such that actually fixes this x, okay. You collect all possible elements of capital G that actually fixes this x, that you call it stabilizer. So, definitely all these elements, okay, of capital G, okay, let us say this is some Gi1, okay. So, let me read it here. So, this is the over counting, so which is G1 x dot x etc. Gn dot x. So, now we have defined this stabilizer of x, okay. So, which is Gx. So, here also I want to put G here because stabilizer with respect to the action of G. So, this way if you write it as Gi1 etc. Gik. So, then what happens for all this Gi1 etc. Gik, the images of x will be x only, okay. So, that means all of them are going to give you one single element, okay. So, in case if you want to group them, okay, then you can from this list if you want to read it out, okay, at some places it will be just x, x and so on. So, that means it should be counted only once because this is obviously over counting, okay. So, then how to do the counting properly, then we will see, okay. For example, for x we see that what elements are giving x. Suppose if this subset of G satisfies something interesting, okay, let us say, okay, actually we will prove in a minute it is actually a subgroup, okay. So, once we know that it is a subgroup, then it is clear that we can talk about left cosets of this subgroup, okay. So, in particularly we have something interesting, okay. We will prove that this is a subgroup, then we can look at all the left cosets. For example, if you take one particular left cosets, call it let us say Gx. So, this is going to be what? Gh, where h is coming from Gx. Now, take some typical element Gh from this coset and apply it on x, okay. Let G in G and h in Gx. Look at this G dot x. What happens to this? This is exactly G dot h dot x, but h dot x is what? X, because h is coming from the stabilizer. So, then this is exactly G dot x. So, this is exactly G dot x. Okay, for all this h, okay, once I fix G, small g, then G dot x is going to be just G dot x. Okay, that means the entire coset is mapped to only one element. Okay. So, you can see that if I relabel this G mod Gx, which has something like, let us say, some G1 Gx, etc., some G D Gx. Okay. So, then we are seeing that G1 Gx is actually gives us, okay, G1 Gx dot x, which is exactly G1 dot x, and similarly G D Gx gives us G D Gx dot x, which is exactly G D dot x. Okay. So, only these elements are going to survive, and we still need to see whether this is again overcounting or not. Okay. So, using these cosets, we see that this collection orbit of x is exactly equal to G1 dot x, etc., Gd dot x. Okay. So, in particularly we got somewhat smaller counting. Okay. So, this is obviously over counting. From this we came down to only this D is going to be what? This D is going to be the cardinality of G divided by cardinality of Gx, if Gx is a subgroup. Okay. So, this is exactly giving us D number of elements, where D is the index of Gx in G. Okay. So, we indeed prove that okay, the following thing. So, we prove that Gx is indeed a subgroup of G, and then the counting that I specified now is exactly that exhaust Ox, and it is exact count of Ox. So, that means the cardinality of Ox is exactly equal to cardinality of G divided by cardinality of Gx. Of course, here I am assuming, for example, G is finite. Okay. Here cardinality of G is assumed to be finite. Okay. Okay, I will stop here and then I will continue with the proof in the next lecture, and I will also demonstrate this using some examples. So, what is important thing to note? Okay, obviously, when you count the orbit, we actually do the over counting. Somehow this over counting should be reduced to correct counting. For that purpose, the stabilizer helps us. Okay. So, that is the thing important that you have to notice. Okay, I will stop here. We will see next class. Thank you.